In this video clip, I'll demonstrate the use of Microsoft Excel for analyzing a truss, planar truss, using method of joints. So starting with a planar truss example, here's a planar truss with a pin joint and a roller support, and that each member listed here, namely BD, AB, AC, CD, and DE are 1 meter, so that goes without saying that AD and CE are square root of 2 meters each. This is the coordinate system that I'm going to use for the entire analysis, but I will have this for each joint or present it each joint as well. For static equilibrium of a truss, each joint must be in static equilibrium, meaning the sum of forces at each joint must be 0, with each joint modeled as a particle. And what I'm going to do now is analyze each joint and come up with the equations in x and y directions, because it's planar truss. So each joint is having sigma f equals 0 as it's a particle, and that sigma f equals 0 means sum of forces in x directions must be 0, sum of forces in y directions must be 0. But I'm going to follow the vector approach, so I'll use I and j's first, and then I'll separate the I and j components to come up with the equation. So if you count the number of joints here, there are 5, and therefore I can only have 10 equations, and there are 10 unknowns. Please note that FAC and FCA are the same forces. Likewise, wherever you see the subscripts the same but in different order, they are counted as one force. So that effectively is the force in that particular member. So for example, FAC and FCA both are representation of tensile force in member AC. But it's just that each joint I have to show tension, and by default I have shown tension at each joint except for the case of support, where I have chosen the positive x direction as the preferred orientation. So once I have shown this, if I get negative, that means the force is acting in the opposite direction to what was assumed. So because I have assumed tension in each member, if I'm getting negative values for forces in members, then those members are experiencing compression. Likewise, if I've assumed r sub ax to point in this direction, and if I get negative value, it means it's pointing in the opposite direction. With that said, let's get started. Here's the joint A with forces shown. The blue are supports, the red are the forces in the members. Starting with static equilibrium of joint A, vector sum of forces must be 0. So r sub axi plus r sub ayj, f sub ab negative j because the positive y direction is up, f sub ac positive I, it's in the positive x direction, plus f sub ad cosine 45 in the I direction, f sub ad sine 45 in the negative j direction, and that must equal 0i plus 0j, or that must equal a null vector which is 0i plus 0j. And splitting I and j's and rearranging terms gives me this form, that r sub ax plus f sub ac plus f sub ad cosine 45 must be 0, r sub ay minus f sub ab minus f sub ad sine 45 must be 0 as well. These are the two equations I get from joint A. So instead of waiting until the very end to create a matrix of equations, I'm going to create matrix just after this slide and update it as I move past each joint. So what you see here is a column of the unknowns, so support reactions and the forces in the members. Again, AB and BA are the same forces, so they are not duplicated, and if you avoid duplication, then you have exactly 10 unknowns and you have 10 equations. So each of these, the list of these forces coincides or is indicating of their position in their row. So r sub ax is the first element in any equation, r sub ay is the second element, and I have to acknowledge the presence of each element in the equation. So when I say acknowledge, in the sense that if, let's say, r sub ax is not in the y direction, obviously, then it has to be shown with a 0. Likewise, if r sub ax is present in the x direction equation, it has a coefficient of 1. Here f sub ac has a coefficient of 1, and f sub AD has coefficient of cosine of 45 degrees, which is square root of 2 over 2. So in the first row, I should have 1 for r sub ax, 1 for f sub ac, and square root of 2 over 2 for f sub AD, which is what you see here. R sub ax is the first element, f sub ac is the fifth element, 1, 2, 3, 4, 5. F sub AD is the sixth element, which has the coefficient square root of 2 over 2. And likewise for the next equation I've written this way. So my recommendation is pause the video clip if you are not sure, write out the equations by hand, and then compare with what I show as the matrix entry. The right hand side is 0 unless I have a number that I can carry on to the or move to the right hand side, and that would be listed in this column here. So all the unknowns are on left hand side, all the knowns are on the right hand side. So in these two equations, they were all unknowns. Nothing was known. As part of this method, we don't start analyzing equations until we have written the entire matrix. So the only knowns will be the external forces acting on the truss, which are given as loads, not supports, loads. Supports are what we are determining as part of this method. Static equilibrium at joint B gives me r sub bx I direction plus f sub bd in the I direction plus f sub ba in the j direction must equal 0. 0I plus 0j. When I say 0, I meant null vector, and that gives me two equations. Although f sub ba is 0, we don't discard f sub ab. We just write that as equation with 1 in front of f sub ab and 0 for the rest, like done here. So fourth element is f sub ab, which has coefficient of 1. The rest of the terms are absent, and therefore 0 is the coefficient that multiplies other variables for this particular equation. Likewise, starting with joint C, doing the static equilibrium, I can write sigma f equals 0 and then get equations, update the matrix. I'm moving a little faster because you know the process now, and you can always go back and pause the video clip to really study this matrix entries properly, and that I don't want this video to be too long either, so trying to minimize time. Likewise for joint D, these are the equations. After simplification, I get this form at joint D and update the matrix entry. Finally, joint E, note that 10 kilonewton is the external force that is known as loading, and therefore it will appear on the right hand side eventually, like such. So note that 10 kilonewton is not written on the left hand side, it's written on the right hand side, and therefore in the matrix entry, here's where that 10 kilonewton load appears. So now we are ready to roll, in that we have a matrix that we have created that would be solved using Microsoft Excel's matrix inverse and matrix multiplication function. So this is of the form A times X, the X column vector equals the right hand side vector B. So X equals A inverse or inverse of this matrix times this column vector. So I'm going to use the Microsoft Excel to enter this matrix and then determine the values for these unknown forces. So let's see how. So starting with a blank Excel file, I will write out all the forces first, but I'll need to have these things side by side. So first and foremost, what I want to do is create joints, or let me just write it this way first, r sub a x or sub a y r sub b x f sub ab f sub ac f sub ad f sub bd f sub cd f sub ce and f sub de. And you can format cells here, alignment, merge cells, wrap text, center, center. Okay, so that's my joint A. Likewise, I can have that for each joint. So in that way, you know which joint corresponds to what equation. Although it was clearly explained in the PowerPoint slide here, but I want to be sure that when you just view the Excel file later, you have you can easily understand without referring to this PowerPoint slide how the number of equations and joints were related. So this is going to be my column vector x. So let me just make it lowercase x and bold, and I'll center that. So and this appears as my column vector b, in bold. So this is ax equals b form, if you will. Now it's just a matter of creating the or writing out the matrices. So it is 1, then 1, 2, 3, 1 again. Square root of 2 over 2 can be written like this, or I can write cosine of 45. So it's cosine of pi over 4, cosine of pi over 4. FBD is 0, 0, 0, 0, and this is exactly R sub A x. And actually I could go about and do this early on. So I'll write equals this guy equals this guy. So it's all covered, and let me just center it a little so they appear as properly aligned, and let me do the same here as well. Okay, so hopefully this reads better for you. Now instead of saying minus of cosine pi over 4, I can just say minus of this value and save time. Then 0, 0, 1, 0. So this is my matrix A. Let me highlight it so that it looks a little better. The problem is that the cells are covered up, but that should not be a huge issue. So that's my matrix A. This is my column vector B. And first and foremost, I have to check whether determinant of this matrix is 0. And the command is mdeter m. The array is this one, and then press shift control enter simultaneously, and it gives 0.5. So because determinant is not 0, the matrix is not singular, and therefore inverse exists. So having taken that lesson from linear algebra, now the solution vector x is determined or computed by multiplying the inverse of this matrix with this column vector b. So first and foremost, select the entire array that I have to populate. So we say mmult, which is returns the matrix product of two arrays, an array with the same number of rows as array 1 and columns as array 2. So mmult And inverse of this matrix means M inverse of matrix A, if you will, multiplied with the column vector B, and then press shift control enter simultaneously, and voila, there we have it. So this is my result, and for comparison purposes I have solved the problem by hand using method of joints, and let's see if I get the same answer as using the matrix approach. So R sub AX, and let's see that here. So R sub AX is minus 20 kilonewtons, R sub AY is 10 kilonewtons, R sub BX is 20 kilonewtons, F sub BD is minus 20 kilonewtons, which is compression. F sub BA is zero force member, so it is 0. F sub AC is 10 kilonewton, it's in tension. F sub AD is 14.14214 kilonewtons in tension. F sub CD is negative 10 kilonewtons in tension. Then F sub CE is 14.14214 kilonewtons, again in tension, and F sub DE is negative 10, meaning 10 kilonewtons in compression. So because I assumed the tension orientation for all forces, those that came out to be negative are interpreted as compression, and thus I have verified that it matches with my hand calculations. But many times if the truss is too large, let's say if there were 20 joints, they would have 40 equations. You may not have time to do all the hand calculations for verification purposes. So in that case, the best way to verify quickly would be to check using truss as a rigid body. So if I've solved everything correctly, I should be able to show that the support reactions computed would be such that it results in the overall static equilibrium of a truss as a rigid body, which means the vector sum of forces must be 0 and vector sum of moments for the entire truss must be 0. Note that truss is considered as a rigid body in static equilibrium, so supports are replaced by support reactions. So sigma f gives me r sub axi plus r sub bxi as oriented earlier, plus r sub ayj plus tan negative j going down. But my computations from using Microsoft Excel have turned out to be these numbers. So when I plug it in here, it's relatively easy to see it is 0i plus 0j, because minus 20 plus 20 is 0, 10 minus 10 will be 0. But what about moments? So let's take moment about A. So if I take moment about point A, I don't have to worry about these two forces. The lever arm is r sub AB, which is 1 negative j, cross with 20 positive I, plus the moment arm going from A to E, there will be 1 negative j plus 2I cross with 10 negative j. J cross I is negative k, but there is a negative sign here already, so that gives me 20k. I cross negative j is negative k, 2 times 10 is 20, giving me that vector sum of moments is 0. Thus I verified that indeed the truss is in overall static equilibrium also. With that said, I'll stop here. Hopefully this was informative and inspires you to play around with different forces on the trusses to see how the forces in the members change. So for this truss, you can put numerous external loadings at different joints and see how the forces will change. Will this force AB remain zero force member? There will be something to explore. Thank you for your time.